All right, let's get started. Let me get the sign-in sheet passed around. I'm actually going to leave the lights on for a little bit. We're going to look at the manual here real soon, and so at least for this first little bit, I want to make sure everybody can see what we're looking at. A couple quick announcements. We have our homework 1 due Monday, so on Friday I'll ask, see if anybody has any questions, although if anybody has any questions today, of course, I'll address them. For Engineering 452, I mentioned this in concrete, I'll mention it in steel. We're going to be doing I'm going to be doing an evaluation of everybody in our program to see who's eligible for 452 and basically what you need to take next semester, if anything, just to make sure that you're on track. So for now, just pay attention to your email. I'll be sending you an email soon. Just look out for it. Today, what I want to do is I want to sort of talk about two things. On top of just sort of closing out our discussion on loads, I want to talk about our first main topic of design, which is tension members. But before we get there, I want to talk about this. Okay, I want to talk about the steel manual. There are some things you need to be made aware of. I want this to not be a scary document. I want this to be something that you can approach. We're going to open it, look through it, and maybe use it today. So I want this to be something that you approach, hopefully not with trepidation, but with interest. Now, last time we had our discussion about wind loads and seismic loads. Well, I think we covered that pretty extensively. Now, remember, there are other load events that we need to consider in structural engineering. Dead loads and live loads being ones that are very, very significant. I will go ahead and tell you that for those of you fresh out of concrete design, or you might remember this, things like live load reduction, I won't ask you to do any live load reduction on any of the homeworks in here unless it's spelled out, like unless we have a problem, it's okay, you need to reduce it. Otherwise, you don't need to worry about it. Assume all that stuff is taken care of. Now in here, dead loads. So we got dead loads, live loads, and snow loads. Dead loads are the loads that are permanent and stationary, the ones that don't move, like the structure's own self-weight, any permanent attachments. The two very, very most common materials that you need to make sure you're aware of, bless you, are structural steel and reinforced concrete. And for our purposes in here, unless otherwise noted, we can take the unit weight of reinforced concrete to be about 150 pounds per cubic foot. Steel's unit weight is 490. You can set your watch by it, so that'll be sort of a constant value that we use. Although, admittedly, we won't use the steel one that much because most of the shapes that we use, for instance, like a W10 by 49, we already know how heavy it is just based on its name. But that'll become clear here in a second. And other dead loads like the weight of the carpet, the ceiling, the mechanical, electrical, plumbing, you can look that stuff up or find it from manufacturers. I don't want to harp on it too much in here because in concrete design we spend a lot of time on this, so I really don't want to harp on it too much. Live loads. So live loads are basically related to occupancy, what the building is being used for. So if we're looking at a school versus a library versus a hospital versus an office building, each of those systems are going to have various floor loadings prescribed to them, which we can look up from ASC 7. So if you're looking at, let's say, a school, you design the classrooms for a live load of 40 pounds per square foot, the hallways for 80 pounds per square foot, etc. And those are pretty easy to find. We did this in concrete design as well, where we actually visualized what a live load looks like. So if you have 150 pounds per square foot, what's that mean? And then that's a lot of people, and so one of the ways that we can improve our estimates of live loads is to reduce that. We can perform live load reduction. So live load reduction is the process by which we take into account the probability that not all of that load is going to be on an element at a given time. And so this is the same formula from concrete design again. You should remember that because if you're in concrete design, we just did it, and if you had it last year, we did that last year as well, so I really don't want to spend too much time on it. Snow's the other gravity load. It obviously depends on where you're at in the country. So higher up north, the larger snow loads. Get down south, you don't have to worry about it too much. And then all the geographic tools are going to tell you the snow load on the ground. You then have to compute the snow load on the roof as a function of your building's exposure, what is its thermal characteristics, and its importance. Remember, we have 4 risk categories, and those risk categories, the higher the risk, the higher the snow load you have to consider. Okay, all right. So really our focus in structural engineering is obviously to ensure that our resistances, how strong the structure is greater than or equal to the loads that we're putting on. As long as the resistances are greater than or equal to the loads, then we're hunky-dory. And so if you want a really basic example, one might be that we want our factored resistances to be greater than or equal to maybe 1.2 times the dead plus 1.6 times the live. And so as long as we've satisfied that expression, we're good to go. So that's what that means over here on the right, the sum of our loads times our load factors. So 1.2 times this load plus 1.6 times this load. So really this entire semester we're really going to be focused on our resistances and ultimately how do we size a member and select a member such that it has enough resistance to carry the loads that we need it to. And that's structural design, period. That's it in a nutshell. The load combos that we use, there's a litany of them that we need to consider, but the most common instances that we would deal with are either 1.4 times the dead or 1.2 dead plus 1.6 live. Whichever one has the highest effect is the one that governs. And in most practical scenarios, equation 2 tends to govern, at least for most load-carrying components in a structure. If you're looking at seismicity or you're looking at wind, you have to obviously consider some of those other effects, but that's basically it in a nutshell. This is something I really don't think we need to spend in class a lot of time on right now, because don't worry, we're going to have plenty of practice looking at load factors and load designs. We're going to be doing a slew of problems in here looking at bolted connections and columns and beams and you name it. And so we'll get ample practice on stuff like this. Don't you worry. What I want to focus on today, like I said, are tension members, this. Okay? Now, has everybody ordered it? It's on its way in. Okay? So one thing I will say, and it was on my analysis slide, but you really want to start bringing it to class regularly. We're going to use it often in here. Okay, we're actually probably going to use it today if time permits. But today I want to go through this a little bit. One thing I will say, some of you, it might still be in the mail or something like that. Feel free to scooch around and sit next to somebody that does. There will be days later on in the semester where it's like week 4 or week 5. And I might go, so what's the answer in the manual? And if she didn't bring hers, I'll call her out or something, because that's what you do when I notice somebody doesn't have their manual. Because what happens is when they don't have their manual, they're really focused on the example and they're sort of like this. And not, well, he ain't going to call on me, is he? All right? Come on. I got to do that at least once. Okay. Let's talk about the manual. AISC stands for the American Institute of Steel Construction. And it is basically the organization, not really so much in the United States, but it's pretty much accepted outside of the United States as the premier organization that represents steel construction, period. This organization does a lot of stuff related to the steel industry beyond just the publication of stuff for engineers. There's a lot of lobbying and funded research and things like that. But by and large, their biggest service is the production of technical resources for people like us, like technical manuals, design guides, and specs like this. And this is arguably the most popular design guide that they produce is the Steel Construction Manual. Now, the steel, look, if you look at this thing has oodles and oodles of different sections. I kind of think of it in 3 main portions, okay? The first part of this manual is sort of the dimensions and material-related values, the base stuff that you need for design. And that's the stuff in the very, very front, the stuff that looks like this. So the stuff on WT shapes, the stuff on channels, the stuff on wide flanges, the stuff on steel grades. That's the stuff that you need for design, okay? Another part of this manual is the actual spec itself. And I think I mentioned this last time. The spec is this region Here, let me see if I can point this out. The spec is sort of this region back here, the one with the gray pages and the white pages that line it. This is the actual code and the commentary. So this is the part of the document that tells you as the engineer, this is how you're going to design. And for every chapter and section in the code, there is a corresponding chapter and section in the commentary. The commentary is the section with the gray line. So if you're opening the spec to section D3, and section D3 tells you to do something, there is a corresponding D3 in the commentary that will tell you why you're doing it. Okay? And we're not going to cover everything in structural steel design by any stretch of the imagination. So when you get out to practice, it's something you need to be aware of, is that you're going to encounter things that we never talked about in school, and stuff that nobody that you know encountered, because that's how engineering is. Engineering is all about tackling problems that you've never seen before. And so make sure that you're aware that, okay, if there's something in the spec, that there's associated commentary that'll tell you why you're doing what you're doing. Okay? So you've got the dimensions and the material related values at the beginning. You've got the spec at the end. Everything in the middle is what you paid for. Okay? And you can tell the stuff in the middle because it's usually very colored, right? You can tell the stuff is colored. It's got these green and blue tables or green and blue axes on the plots and so on and so forth. This is what you paid the money for. These are the design aids and the guides and the tables and charts that we use during the design process. And this is where the money went to. In this course, we are always going to use the blue numbers, not the green numbers. Okay? Remember, there are two philosophies upon which we design structures. One of them is LRFD, which what we're doing in here, the 1.2 dead, 1.6 live, where you factor the loads and you factor the resistances. The other is allowable strength design, where you just use like a factor of safety of 3, or 2.5, or what have you. The steel industry has, in their publication, sort of combined the two into a single document, and the way that they delineate that is the green numbers are for ASD and the blue numbers are for LRFD. It's not like the behavior changes or even the nominal capacities change, it's just your factors, okay? So for us, just so that we're consistent and whatnot, we're going to use the blue numbers. Like in concrete design, there is no green and blue numbers, they just go with the blue. The bridge spec goes with just the blue numbers, if you will. So we're going to stay consistent, and that way we don't have to deal with a bunch of different philosophies. So we'll always use the blue numbers in here. So just something to keep in mind. Okay. Let's talk about steel as a material, and let's talk about some properties, some material values, dimensions, some things that you need to be aware of. How many of you remember this from 216? Maybe you saw it in 321. The stress strain curve for steel. This is one of the most fundamental curves that we generate in engineering, one of the most fundamental data sets, the stress strain relationship of structural steel. It is also really fundamental to our understanding of how we do things as structural engineers. Now, you might not have heard this before, but so one of the things about structural steel is that it's very, very ductile. It has the ability to withstand a lot of inelastic deformation. So remember, the difference between inelastic and elastic deformation is elastic deformation is like the rubber band. You take a rubber band, you load it, you let it go, it goes back to its original shape. That's elastic. Inelastic deformation is sort of like what happens with a Coke can. Like if I have this can and I take it and I squeeze it a bit, snaps back to its original shape. But if I take this can and I wail on it, it's a crushed can. It's stuck that way, right? That is inelastic deformation. Inelastic deformation is everything past the yield point. Now, I heard this really brilliant description of the ability of steel to be ductile related to a football field. So imagine that this is a football field, right? And so this is one end zone, right? Right here, and this is a football field. From here to here, that's about the 1 yard line. So in other words, steel's rubber band-like behavior is only from the end zone to the first yard line. in terms of its ability to withstand inelastic deformation. From here to here, that's about the 10-yard line. So that's that perfectly plastic behavior where it just freely deforms until it catches up and it starts to strain harden. That's the other end zone. That's the whole other end, to give you kind of some scale. So steel has a really remarkable ability to withstand some very significant inelastic deformations. It's an extraordinarily ductile material, which makes it a material of choice when you have significant inelastic demand, like in earthquakes and things like that, as long as you're doing your detailing appropriately. Remember that once you get into inelastic land, remember, if you take the load off, remember how it unloads according to that same slope being the Young's modulus, or the modulus of elasticity. That modulus of elasticity is a very, very critical term. It relates how much steel deforms as a function of how much load we put on it. It's a very fundamental property, and it does not change from grade to grade. Dependent upon your steel grade, E, the Young's modulus, will always be 29,000 KSI. Also, the unit weight of structural steel, again, will always be 490 pounds per cubic foot. That number E equals 29,000 KSI, that's a number I want burned into the back of your head by the time this is all said and done. Okay? By the time you all graduate, that's a number I want you to recall from memory. Just like the unit weight of water, 62.4 pounds per cubic foot. Okay. Now, what does change from grade to grade are the yield stress, in other words, the point at which the steel, or the point at which the can goes from bouncing back to being permanently deformed. That's the yield stress. And then the ultimate tensile stress, sort of the maximum stress on that stress strain curve before the sample begins necking and ultimately fractures. That does change from grade to grade. Now, where do you find that information? Like, what is the yield stress and the tensile stress for a given grade of steel? You find it here. Specifically on page 2-48. Let's open our manual to page 2-48. So, if you open your page to 2-48, you should see a table that looks something about like this. Now, a little bit about the anatomy of the manual. If you look on the side and you see those black and silver tabs, you can count. And so the second, like there's one that says DIM, that says dimension. All of those pages will be like 1-something, 1-5, 1-6. The second tab should say GEN, stands for general design considerations. And so that's the second section. And so if you go to page 48, that you should see something that kind of looks like this. Does everybody find that? Okay. Now, I mentioned this earlier this semester, and I'll mention it now. In my notes, see how I've got this little star for that tab, or for that page? If you notice in my manual, I have a little tab right here. This is a table that you will use a lot in here, is table 2-4. So if I were you, I would place a little sticky note, a tab, a label, something here, however you want. I mean, you don't have to, but I would place something here so that you know where this table is, because we will refer to this a lot, okay? What this does is this lists the material properties for given grades of steel. So for example, if I'm looking at A501 grade A steel, what's the yield stress? A501 grade A.
36.
There we go. Grade 30 is 36 KSI and ultimate tensile stress. A501 grade A. 58. And that's where this is. Okay, so that material is here. I'm telling you, I'm going to give you problems. I'm going to say, okay, A992 steel. And I'm just going to say that. I'm not going to tell you what FY or FU is. You've got to find that out, because that's how it is. You spec out a steel, and all those material values are known. Now, some of those are listed as a range. In other words, if you look at grade A36 steel, we have the yield stress is 36, but the FU is listed from 58 to 80. Okay? Now, I'll tell you why it's listed as a range here in a second, but let me ask you a question. If you're in design mode, If it says the tensile stress is anywhere between 58 and 80, what do you use for design purposes?
58.
58. Exactly right. You use the minimum, right? Because that's the worst case scenario. If you're designing, if this is going to be a bridge that holds up or that carries traffic and your grandma's going to be driving over this bridge every day and you don't want anything to happen to grandma, you pick the worst case scenario. And the worst case scenario would be 58. Okay? And so the question might be, well, why put the range? Why not just put 58, right? The reason why is because for this particular grade, grade 36 steel has a way of exhibiting different ranges of ultimate tensile stress. One of the things about just material science in general, the larger the strength, the lower the ductility. And so A36 steel might not be as ductile as you need, and so they report that range basically so that you understand that that could be an issue in earthquakes. In 1994, the Northridge earthquake happened, and there was a lot of structural steel frames that the community thought would be fine, and then they, after investigation, went, oh, they cracked and fractured all over the place because they weren't as ductile as we thought they were. So that's why those ranges are reported. So just a food for thought. But yeah, in design mode, when you're designing tension members and connections and things like that, use the lower value. That make sense? Okay, that's important because that will come up. Okay, now let's talk about the types of steel products that we deal with in structural engineering. So right off the bat, we will be handling or dealing with problems where it's just plate, like we're designing a connection for a half-inch thick plate, or looking at bolts and welds and things like that. So those are very common sections. But as for the rolled shapes that we're looking at, see, when I say rolled sections, what I mean is, so you have a, essentially molten steel, cast that into billets, and then you're using high-pressure rollers to compress that into a channel or an I-beam or an angle or something like that. That's what I mean by hot-rolled steel. Hot-rolled steel is what we're looking at here. One of the things that you will never hear me say when I'm talking about speccing out shapes is an I-beam, okay? I might use I-beam when I'm talking about like behavior and bending and things like that, but you will not find I-beams in here because there's a slew of different types of I-shaped cross-sections. For instance, we have HP sections which are used for piles. We have W sections which are used for beams and columns and things like that. So we're a little more specific. Arguably, the most common cross-section that we use is a W shape. W stands for wide flange. So it used to be called WF shapes, now it's just W shape. But W shapes are arguably the most common cross-section that we deal with in here. We also have M shapes for miscellaneous. We have S for standard I shapes, but they're not as common. W shapes are arguably the most common. For some terminology so that we're all speaking the same language, if I have an I-shaped cross-section, if I'm talking about this top and bottom portion, that's called the flange. So I have, like, this is the flange, that's also the flange too. So those are the flange, and then the center portion, we call that the web, okay? So I'll be using terms flanges and webs, pretty regularly, so I want to make sure everybody's aware of that. If we're talking about angles, that's the leg of an angle. That's what those are called, angle legs. So just so everybody's aware of the phrases and the terminology. Let's look at part one. Okay, so I want everybody to open up their manual and turn to part one. You can turn to this page. It doesn't really matter what page, but I'd like you to turn to one of the W-shaped sections. Any one of them, it doesn't matter. Here, you're welcome. Now, I have here on my slide, just from a logistical perspective, I have here on my slide something for part one. You're a little, you need to be that. So is everybody here? I see, for the most part, everybody's getting there. Everybody's getting there. There we go. There we go. So, okay, first off, when it comes to tabs, I don't think you need to tab every single table. I think you should probably tab a few. I-tab, the W table, the channels, the C table, the L table, the angles, and then the WTs. That's what I-tab. You can tab as many as you want. I mean, you can do what you think is appropriate. But that's how many I-tab. Again, I don't think you should get tab happy, just what you think is enough for your references. Okay. Now, if you look at this table, what this table does is it lists the dimensions of each of these shapes, and it lists them a couple different ways. First thing I want you to notice is that it lists everything, okay? So for instance, if I'm looking at a W27 by 129, for example, it will tell you the cross-sectional area, how deep it is, how thick the web is, the flange, what is the width of the flange, the thickness of the flange. That's the page on the left. The page on the right, it's all the same table. So, like for instance, if you're looking at a row on the left, the row on the right, that's just the same table continue. If you look, you can see like where it says, if you're on W27 by 129, on the next page it'll say 129 and those properties keep continuing. So on the right page, it'll list like moments of inertia, it'll list like torsional properties, all sorts of stuff, okay? Yes?
What are the like C's and H's and CV's?
That is a great question. So the question was what's going on with the little C's and the H's and the V's? What I'll say about that is this. That'll become a little more clear when we talk about columns and beams, but the short, quick, and dirty answer now is when you have things that are in compression, like things are being pushed on, things like the buckle, right? And so in structural engineering and in steel design, we really are focused on two modes of buckling, either global buckling or local buckling. Now, global buckling is if you have a column in a building and you push it and the whole thing bows out. That's global buckling. Local buckling is instead of the whole column buckling out, maybe a flange crinkles or a web crinkles. Those notes where it says like C, what it's saying is that the flange or the web might crinkle when subjected to compression. And so the C is for compression, the V is saying it might buckle and shear, the H is saying you might have a local buckling issue for bending and things like that. It'll become important later when we look at columns and beams. For now, it's really not going to be an issue. But it will be important later. That's a great question. Any other stuff? This is great stuff. All right. Now, when you look at some of these dimensions, you've got a couple choices. Like for instance, if I look at the depth for a W27 by 129, it says 27.6 and then it says 27 5/8. What the heck's going on here? Which one do I use? Okay.
Rounded, right?
What's that?
Just rounded.
Well, exactly right. So basically, whenever you see the fractional value is meant to be the value used for detailing. So if you're drawing this thing up in AutoCAD or MicroStation or something like that, the idea is that you use the detailing value. And the reason for that is if I'm out on the job site and I got myself a tape measure and I pull it, it's going to say 27 5/8, okay? But the design value is a little bit more accurate. So as these sections are getting rolled, the distances are being recorded to a various specificity. And so think about it like this. The decimal values are sort of recorded to three significant figures. The detailing values are to the nearest 1/8 of an inch or 1/16 of an inch for the purposes of drafting and detailing. When we're doing calculations in here for design, we use the design values. We use the decimal values. When you're drawing it up in MicroStation or you're out in the field checking distances, you use the detailing values for drawings and drafting and things like that. Okay, is everybody okay with that? Now, I'm going to tell you somebody in here is going to use a fractional value, and I'm going to go, don't do that. But just wanted to throw that out there. Always use the decimal values for design. Okay? Sound good? All right. Now, for terminology, I don't know if you've heard this in 321 or some of your other courses. Maybe you've heard this before, maybe you've not. But I just want to make sure everybody's on the same page. When you name a shape, there's three terms. So like for instance, there's the W, which tells you it's a W shape or a C shape or channel or WT, what have you. There's the number, the first number. So for instance, on the board here, I have a W10 by 49. The 10 is what we call the nominal depth. It's about how deep it is. It's set basically to the rolling schedule. Like if you look at all of these W27s, they're not exactly 27 inches deep, but they're about 27 inches deep. They're about how deep they are. So the first number is the nominal depth. The second number is its weight. So a W27 by 129 would be a wide flange section that is about 27 inches deep and weighs 129 pounds per foot. Okay? So you never need to calculate the self-weight of a rolled section, because if it's a W10 by 49, it's 49 pounds per foot. That's how they're spec'd out. So if you're trying to determine beam self-weight, it's really easy in here. It's just the name of the section. Okay? Any questions? Are we good? Let's get into some fun stuff. Now I'm going to turn the lights on. Oh, we got plenty of time. All right. So in this course, we're going to look at a series of different types of members in buildings, and we're going to learn how to analyze and design them. Now, arguably the most common type of element in a building or even a bridge are beams and columns. Okay? So stuff being bent and stuff being pressed on. I mean, look at a building. We have columns here and beams there. We're actually going to cover that last. The reason why we're covering it last is because there's a lot of behavior stuff that you got to understand, and then there's a lot of stuff you got to be familiar with the manual. Okay? What I want to do is I want to ease you into it. I want to take our time, cover something that's pretty simple, but can ease you into getting used to this and to getting used to the design process. So we're going to start with what is arguably the most basic element of design, which is a tension member, something being yanked on. Okay? So we're going to talk for our first part of our course about designing tension members. Okay? They are among the most basic of structural elements that can be found. They are in just about every building. If you've got a truss, the tension members are going to be the truss members that are experiencing tension. They're used as braces in buildings under lateral load, under wind and seismics. It's a very natural place to start the class because we can learn about the design process and we can become familiar with the manual. Now, what we have to do for a tension member is we have to first go back to mechanics. So the mechanics are pretty straightforward. You take a piece of steel, you yank on it, right? What's the stress? P over A, right? Force per unit area. So if the stress is P over A, what's the maximum force? Well, it's some limiting stress times the area, right? That's about it in terms of the behavior. That's about as complicated as it gets. Now, there are some detailed phenomena that we need to discuss about gross sections and net sections and shear lag and things like that, but the overall idea is no more complicated than that. Now, in structural engineering, what we have to do is we have to define a condition that's called a limit state. So a limit state is a condition that we as structural engineers define such that if we go beyond that condition, we no longer fulfill relevant design criteria. And so we tend to have two different types of limit states in structural engineering. Those are strength limit states and service limit states. Strength limit states are more related to safety. In other words, if I exceed that, we're killing somebody. Okay? Service limit states are meant for more day-to-day performance. We're going to look at both types of limit states with tension members, but they're more for day-to-day function. Things like deformation, human discomfort, construction tolerance, so on and so forth. Just stuff that makes the structure easier to put together and performs well under its service life. Don't worry, we're going to assess both. But a limit state is a condition upon which we violate that, the structure or the component is no longer fulfilling its purpose. And so those limit states are going to be essentially how we design a given member. And so the easiest way to understand what a limit state is to just take a tension member and ask yourself, what are the different ways that that tension member could start to behave outside where we would want it to behave? And the limit states are pretty easy to understand when you think about it. So I got this piece of steel and I'm yanking on it. So I'm taking it and I'm pulling it like that, and I'm pulling it like that. At what point does it start to experience failure? Well, the first is yielding, and we call that yielding in the gross section. The gross section is just a fancy term for the main body of the member. And it's a pretty, I'll say, boring thing to look at. I don't say it's boring. It's just basically the member just getting longer. I have here a video of a piece of steel being yanked on, and this is what it looks like when it yields. So we have the steel, it's being yanked on, and basically, again, it's like the Coke can. Once you crush it and once you exceed those stresses, it just gets longer and, you know, those deformations become permanent. Now you can see, did y'all notice how, like, from beginning to end, how that thing got really long? Like, let me replay that. I mean, look at this from beginning to end. That sucker stretches something fierce. That's what it looks like before the test. That's pretty long. It's starting to stretch out a good bit, right? Now imagine if this tension member was 20 foot long. How much deformation do you think that'd be? That'd be a lot, right? Because remember, we're talking about strain, right? The change in length divided by the original length. So if the member gets longer, that deformation gets even bigger. And so in the gross section, we actually would prefer that it doesn't yield, and so we limit the gross section to the yield stress. So our capacity is defined by, remember, a limiting stress times a gross area, right? Make sense? Now, remember, here's our fundamental expression, right? We take a nominal capacity, we have a nominal capacity, but we then adjust it by this safety factor phi, right? So for gross section yielding, our phi value is 0.9, okay? You'll see where I'm going with this here in a second. Can I borrow the manual real quick? Now, this comes from the specification. So I want everybody to turn in the manual and see where this is. So here's the manual. I'm going to this back section back here, this section in front of the gray, okay? And I'm at 16.1-28. I want everybody to turn to this. I'll wait, because this is important. Oh, you're a little bit further ahead. About. There you go. Keep going. That's 33, so a couple more pages. There we go. All right. So we're in the specification and we're in Chapter D. What is the name of Chapter D? Somebody tell me. 28. What is the name of Chapter D?
Design of members for tension.
So it looks like we're in the right chapter, right? And so if you look at section D.1, section D.1 is related to slenderness. We're going to talk about that a little later. Section D2, tensile strength. And so what does it say? Here, let me read this out. It says the design tensile strength and the allowable tensile strength. So the allowable is related to allowable stress. We can ignore that. The design tensile strength of a tension member shall be the lower value obtained with these following two expressions. And we have for yielding in the gross section and for rupture or fracture in the net section. We're going to talk about that here in a second. And so we have our expression. Our nominal capacity is the yield stress times the gross area, and our phi factor of 0.9. So if you're looking at this expression, what's phi RN for gross section yielding? 0.9 times FYAG. Now, that's gross section yielding. What about net section fracture? Well, a couple things are different. First off, we're not talking about the main body of the member. We're talking about the net section. And so if you're curious or if you didn't understand what the gross section was, Well, I think when you look at the net section, it makes a lot more sense. The gross section is the main body of the member. The net section is right there around the connection, right? So if you're looking at a tension member and you're yanking on it, I think it makes sense that it's either going to fail in the member or it's going to fail at the connection, right? So one of the ways that it can fail at the net section is by fracturing. And so what does that look like? Here's what it looks like. So here's a member that's being fractured. So you can see, obviously, we've got the connection, we've got bolts we've got to consider. We're taking this and we're yanking on it. You can see how the color's changing. You can see it starting to yield, but it's not stretching as much. So we actually don't care if it yields around the connection because there's just not much there's not much room for it to deform, but that's obviously what we care about. We care about it actually separating in half. Now, if we look at our expression, hold on, if we look at our expression, so there's a couple things that are a little different. It's a similar formula, although we're not limiting it to the yield stress, we're limiting it to the tensile stress, so the stresses are different. Instead of the gross area, we're looking at this net area, or more specifically, an effective net area. We'll talk about that later. But look at our phi value. Before our phi value was 0.9, now it's 0.75. Okay, let's think about that. These phi values are resistance factors. They are lowering the amount of capacity we can use. In other words, we calculate our capacity, but then we reduce it with these phi values. Now for yielding, we got a phi value of 0.9. But for fracture, we got a phi value of 0.75. Now let's think about that. If I have a building and a member yields, yeah, it sucks, but it doesn't mean it's separated in half, right? If it fractures, I'm literally taking the member and splitting it in two, right? That is obviously a worst case scenario. That is a worse situation. So much so that my phi value has dropped. Instead of a phi value of 0.9, I'm using a phi value of 0.75. All right? That'd be worse. So we account for that by using a more stringent resistance factor, so the capacity would be lowered. Now, how do we compute this effective net area? It's a function of two things. It's a function of the net area, and it's a function of shear lag. I'll tell you right now, on your first exam, there are two things that's going to cause you a challenge. Net area and shear lag factor. You understand that, you understand tension members. Go ahead and tell you right now. And don't worry, we'll delve into these in very significant detail. All right. The last limit state that we're going to discuss is kind of a weird one. It was kind of found actually by accident in the lab. It's what's called block shear rupture. The best way to describe it is to just show it to you. So here's a block shear rupture test. What happens in block shear is you don't fail so much in fracture, but what kind of happens is you have this sort of combined failure where you have a little bit of a tensile failure and a little bit of a shear failure, and you kind of rip a chunk out of the section. Did y'all see that? Let me play that again. So you're going to fail in tension here and then in shear here, and it's almost like that entire chunk gets ripped off. Everybody see that? That's what's called block shear. It's sort of a unique one. We're not going to look at block shear until the end. The equation for block shear is not hard, but it's very involved, and so I'll wait to show you that till we get towards the end. If I showed you that equation versus these, you'd go, because it's pretty big. But it's really not hard. You just need to understand some basic concepts, and we'll get there. Now, there are a couple of other ways that a member could fail if it's being yanked on. Maybe the member does just fine, and it's not the member that fails, but it's the bolts that fail. Maybe the bolts fail, or the welds fail, or the plates that it's connected to. Like if you're talking about a tension member, it's in a building, it's connected to something else. Maybe it's those adjacent elements that fail. And we'll talk about connections and connecting elements later. We will cover it, just not right now for tension members. So for right now, during our tension member discussion, assume that the bolts are made out of adamantium or vibranium or something that's not going to fracture. That's perfectly rigid. Later on, we'll discuss, okay, how do the bolts fail? How do the adjacent plates fail? But for now, we're just not going to worry about it. All of that stuff that I discussed, that was strength limit state. We do have one service limit state that we will discuss, and that's slenderness limits. Basically, if a member gets too slender, it gets too flimsy, and it kind of gets hard to handle during construction. So we have a slenderness limit. We'll talk about what slenderness is later. Okay, before I move on, are there any questions? And I know I threw a lot out at you, and that's fine. I mean, we're going to take all of that stuff and very, very slowly digest it. But before I do, any questions? Okay. All right. Let's talk about gross area and net area. Okay. So we got gross section yielding and net section fracture. Basically, if you understand gross and net area, you're halfway there. So we're talking about areas. Why are we talking about areas? So remember, stress is P over A. So that area, that cross-sectional area is very, very important. If we're talking about steel, you have the member and you're drilling holes or punching holes into it to create a connection. So if I samurai sword or lightsaber through that section, it matters if I'm cutting like right here versus in the main body of the member. I get a different area because I'm cutting through bolt holes. So we've got two different cross-sectional areas. We term those the gross area and the net area. So how do you compute that? Well, the gross area is pretty easy. You're either looking it up or using some basic geometry. The net area is sort of a new one. Now, in general, the net area is defined as the gross area minus any area that you have lost due to the presence of bolts. Okay? Now, a note on terminology. If you ever hear me use the term a line of bolts, lines of bolts run parallel to the stress. So I would be yanking on it this way, so the lines of bolts go this way. So I've got 2 lines of bolts in each flange, and each of those lines have 5 bolts in it. Make sense? Okay. Now, how many of you have ever, and we're probably going to have to close on this, how many of you have ever done any sort of mechanic work, worked on a lawnmower, like tried to fix a lawnmower in your parents' garage, or any type of work with cars or anything? How many of you have ever done anything? Now, what happens if you have a bolt that's a 1/2 inch in diameter and you try and stick it in a hole that's a 1/2 inch in diameter? You're shaking your head. What's that? It doesn't go, right? The hole actually has to be a little bit larger than the bolt, right? You have to drill it a little bit larger, okay? Now, what we do in here when we look at bolt diameters and hole diameters, the way that we compute that is we take, if we want to determine the hole diameter, we take the bolt diameter and we add 1/8 of an inch, okay? That's what we do in here. There's 2 reasons why. We add 1/16 of an inch because the hole is actually 1/16 larger than the bolt. That's the physical dimension. So if you have a bolt that's a 1/2 inch in diameter, the hole is 9/16 inch in diameter. Standard holes in structural steel design are drilled 1/16 of an inch larger than the bolt. So you have to drill it a little bit larger. Okay? Now, how many of you have ever actually drilled a hole in steel before? Have you ever actually seen what it looks like? You got the burrs and it's all kind of rough, right? So we add 1/16 of an inch to account for the fact that you actually have to drill the hole a little bit larger. We add another 1/16 of an inch because we assume that this little lip of material around the hole is not really that effective in transferring load to the member as a whole. So whenever we look at a steel section, when we compute the hole diameter, we take the bolt diameter and we add 1/8 of an inch. What we're really doing is adding a 1/16 twice. One for the fact that the hole is actually bigger, or what I'm calling erection tolerance, and one is for the fact that that little lip of material is somewhat damaged and not really effective in transferring stress to the section as a whole. Nudge, nudge, wink, wink might be a problem on a celebration of learning. That was your freebie. Why do you... There you go. Look at this guy. He's like, I ought to write that down. Why do we drill, or why do we add 1/8 of an inch to the bolt diameter when computing the hole diameter? Why do we do that? I don't know. Okay. Sound good? All right, we're running out of time, so we're going to call it here. What we're going to do as soon as we show up on Friday is we're going to compute the net area. Now I want to show you what we're going to do on Friday. We're going to compute loads of net areas. We're going to focus just on that. And what gets challenging is this. Our first two examples are going to be like this, where you have these grid-like rectangular patterns of bolts. But what happens when the bolt patterns look like that? What happens when they get staggered? So computing the net area for a parallel bolt path versus a staggered bolt path gets a little confusing, and you have to consider the possibility of fracture along, different possible failure paths. And then you have to also consider, well, how do I compute the area along a path that's diagonal? And the way that we do that is through the presence of stagger factors. So if you remember, I said in general, net area is the gross area minus the area loss due to bolt holes. Well, we're going to take that formula and refine it a good bit because to account for the presence of a staggered connection. That's what we're going to do on Friday. So make sure you bring your manual. Make sure you bring calculators, all that. We're going to do some math together. That's all I got. I will see you all on Friday.